Welcome to this latest video on revisiting floating point. We'll be looking at normalization of floating point, we'll be looking at floating point arithmetic, and we'll be looking at converting a denary number into a floating point representation, both positive and negative, and of course turning floating point into denary. The first question here, these are all exam questions from the OCR exam builder. And the first question we're looking at is a real binary number. Real means something in this context, does it not? It means it's a number with a decimal place as opposed to an integer. So a real binary number may be represented in floating point notation, 7 bits for the mantissa. In fact, you know what? Why don't I just zoom in a little bit here? There we go. 7 bits for the mantissa followed by 5 bits for the exponent. And both are in 2's complement, allowing us to store them as either positive or negatives. State which of the binary of the numbers p and q is normalized. Well, what I'm going to do first of all is I'm going to look at these numbers here and extrapolate mantissa versus exponent. Now mantissa was 7 bits, so it should be these first 7 bits. So 1, 2, 3, 4, 5, 6, 7. And I'll highlight the mantissa as being in yellow. So that's the mantissa. And then what's left, the other 5 bits, well, that would be exponent. And I can do the same for the other one. Those first 7 bits I'm going to do in yellow to represent mantissa. And for the other side, I'll represent as exponent. Now, normalized means something in this context. It should be in the format of 0.1 something if it's positive, and 1.0 something if it's negative. So 0.1 something if it's positive, and 1.0 if it's negative. And the point by default should be here. Now, if we look at this number here, it's 1 something 0. So we can imagine if there's a point there. Is that normalized? So looking at these questions, we can see that the position of the point should be between the first 2 values here, between the most significant bit and the one before it. And that would be 1.0, meaning it is in a normalized form and a negative number. For this one, for q, the point would be between 1 and 1, thereby meaning it is not normalized. In fact, what we'd have to do to normalize it is to do what? Move the point 1 over here, and then because that would involve the mantissa becoming larger, we'd have to decrease the exponent by 1. So we can say to be normalized, the mantissa should be in the format of either 0.1 or 1.0 for the first 2 binary values. P is in this format. Whereas if we're going to talk about Q, what are we going to say? Whereas Q is 1.1, which is not normalized. The follow-on question is that the binary number r is not normalized. So it's not normalized in this context. Write the normalized form of r. You must show you're working. So I guess first of all, we'd have to determine, do we think this is going to be a positive or a negative value, this one here? What's our thoughts? Well, being that it starts with a bunch of zeros, it indicates that it'll be a positive value. If it started with a bunch of ones, it's a negative value. Remember, the default position for where the point is it's between these first 2 values. Where are we going to have to move the point for it to become normalized? We have to move it to the right by how many places? There we go, once, twice, and then we can rewrite it. Now, I didn't actually read from earlier, presumably we're still under 7-bit mantissa, 5-bit exponent for this. But let's just write out the mantissa. In fact, if I try to be consistent, I said that was in yellow. Ooh, that's... Okay, so 0, 1, 1, 0, 1. Oh, it's actually in it. So these first 7, see, if I highlight it, these first 7 are the mantissa, and these are the exponent. So I've got 1, 1, 0, 1, and now I've run out of values. By the mantissa moving 2 to the right, has that made it larger or smaller? It's made it larger. Therefore, the exponent has to become smaller. And currently the exponent is, we can see here, 1, 2, 4, 8, 16. What's the last one going to be? Oh, in fact, but the last one was negative 16. I've lost track there. Yeah, negative 16 because it's in 2's complement. So the current value of the exponent is 5. We're saying it's getting smaller by 2, so the exponent is now 3. There we go. So the exponent would be 0, 0, 0, 0, 1, 1. No, I put too many zeros in there. Apologies, people, because it's a 5-bit Mantissa. There we go. What about this Mantissa? Is it working well? Yeah, we need to pad with zeros. How many bits is the Mantissa? 7. So we've currently got 5. There we go. So if I was going to write it out, I should write this and this next to each other. So the answer would be 0, 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 1. So that bit's here and that bit's here. So looking at this question here, we are looking at now converting a denary value into a floating point binary value. We're going to represent the number 55, but the format we need to represent it in is a 8-bit Mantissa followed by an 8-bit exponent. And both will be in 2's complement. And if you remember what I said previously, even if they don't say it's 2's complement, you should assume it because most values can be held as negative or positive. So how are we going to do it? Well, if you remember, if we have the value 55, the very first thing we want to do is put it into fixed point. To put it into fixed point, I'm going to draw the, I'm going to write out the grid for a fixed point value. Bearing in mind I'm needing to make it large enough to store it. Currently, this is going up to 31, so I need more. Oops, that is not intentional, apologies. So I'll go to 32. And when I go up to 32, I do have enough values, but my most significant bit cannot be 32 because it's going to be in 2's complement. So it should be 64 I'm going to need, aren't I? Yeah. On this side, you know, I could put a half and a quarter and go off in this direction, but how many of those things do I actually need? Yeah, well, I mean, like, because I'm only going up to, it's a whole number value, isn't it? I happen to be converting. So I'm going to put 55 in it. So I'll say, how many 32s go into 55? Well, 1, leaving me with, oh dear, math and spot, 23, I believe. And then 16 would fit into that, leaving me with 7. Excellent. And then 0, 1, 1, 1. And on this side, it will also be zeros. And that would be a 0 for the negative. Okay. The next thing I'm going to want to do is turn it from fixed point into floating point. It has to be put into standard form like we looked at normally. It has to be normalized. So it's either 0.1 or 1.0. Which will it be? 0.1 because it's a positive value. So this point here, instead of being fixed, we'll need it to float all the way over to here. So that's 1, 2, 3, 4, 5, 6. 6 times it's going to go across. I'll also draw it. So I'm going to go once, twice, 3 times, 4 times, 5 times, and 6 times. And then I'm going to rewrite my Mantissa. So that would be 0.110111. In my case, I put 0 here. 0 obviously is not necessary to include that, but I did put it there. By moving the point 6 times to the left, have I made the Mantissa larger or smaller? If you're ever struggling to it, remember the rule. If you've got here, you've got 1.7. If I moved it once to the left, it'd be 0.17. Did that make it bigger or smaller? Smaller, right? Because by moving that point 1 to the left, I've made the number smaller. Same with binary. By moving it 6 to the left, you've made it smaller. Yeah, by a factor, well, 2 to the power 6 smaller, yeah. So therefore, I need to increase the exponent. And the exponent, because it's in fixed point, we're at 0, so now I need to make it 6. And at this point, I need to start paying attention to how many bits for the exponent and Mantissa. How many bits for the exponent? 8. So I can on one side do, I could do, for the exponent, I can say 8 would be 0 1s, 0 2s, 0 4s, Oh no, wait, what am I talking about? I'm trying to do 6. What's wrong with me? 0 1s, 1 2, 1 4, that makes 6. But I can't stop there, can I? Because how many bits for the exponent? We said it was 8. Sure do. 1, 2, 3, 4, 5. On this side, how big was my Mantissa? Well, it's also 8 bits, so I'd go 2, 4, 6, 8. Oh, there's only 9, so I'm actually close. So if I was going to write it down, I'd say it's 0, 1, 1, 0, 1, 1, 1, 0, because that's going to be 8 bits long. So I've basically lost this one. And then on the other side, 0, 0, 0, 0, 0, 1, 1, 0. With an 8-bit exponent, you can make some truly colossal numbers or some very, very teeny tiny ones. In fact, it would be 2 to the power negative 128. 2 to the power negative 128. That is little. Okay. We're continuing with our exploration of denary into floating point. This time here, let's explore what might be different. Well, a couple of questions. Using normalized floating point binary, like we just done before, but now it's a 4-bit Mantissa and a 4-bit exponent, represent the denary value of 1.75. You must show you're working. So same deal, we'll put it into fixed point. Once we put it into fixed point, we'll then move the point, being as that this is a positive value, to make it 0.1. And for this one, lower down, you can see it'll be a negative value, but we'll also have to turn it into a 2's complement negative version of it. Okay, give that a try. Okay, let's look how we're going to answer this question. First thing we want to do is to put it into fixed point. So let's do that. I'm going to put out 1, 2, negative 4, because that'll get us to the number we need. On the other side, we need half, and we're going to need a quarter, okay, because it's going to allow us to represent the value. So none of those, one of those, one of those, and one of those. What we're going to want to do is to put it into normalized format. We're going to have to move that once to the left, giving us a Mantissa of 0.111. The exponent, because the Mantissa's become smaller, the exponent has to become larger. It's a 4-bit exponent, so in that case it will be 0, 0, 0, 1. And so if I was to write out the answer, I'd write it out in the format of this. Of course, I'll omit the point, because the point is always between the first two, and that's how I do it. Now, for the second question, it's asking you to do negative 1.75. So what we'll have to do is we'll have to put it into 2's complement. So we'll start off, I'm going to start off with the original fixed point of 0, 0, 1. In fact, I don't even need this first 0, do I? I can get rid of that. There we go. 0, 0, or maybe I should do it because I'll have to do something then. So 0, 0, 1, 1, 1, like that. If you remember to put things into 2's complement, the first thing you need to do is flip them, putting it into 1's complement. So everywhere there's a 0, it becomes a 1, 1 becomes a 0. So that's 1, 1, 0, 0, 0, 0. Then you have to add 1 to the least significant bit, i.e. add 1 to this side. So I'm going to be, no, I won't be lazy. I'll make the effort for you guys. Plus 0, 0, 0, 0.01. So that'll give me 1, 1, 0, 0.01. You can also check it. So it's negative 4 plus 2, make negative 2, plus a quarter, negative 1.75. It is also not in standard form. I'll take this point and I'm going to move it here, right? I don't want to move it here because that's not standard form, right? It's going to move here and then I'll lose this 1 because that 1's not actually giving me any useful information. Effectively, instead of being negative 4, 2, I'll make that the negative 2 because that'll be the most significant bit, this one here. So I'll move this over by 1. There we go. The Mantissa, as I write it out, will now be, well, it was going to be 11.001. This bit here, because that is no longer giving me useful information, I will now remove it, and it has gone. And then for the exponent, because I've moved it once to the left, same as last time, I've made the Mantissa smaller, and therefore I need to make the exponent larger. So the exponent would be in the same format, 0, 0, 0, 1. And I'd write out the answer like this, 1, 0, 0, 1, 0, 0, 0, 1. Yeah, another question we're going to do here on denary into floating point. variables in a program contain specific data types, real, integer, etc. Show the denary number -2 and 5/8. Let me write that out because it's not that easy to read. So that's -2 and 5/8. You need to show that as a floating point number with a 6-bit mantissa and a 4-bit exponent, both stored using 2's complement representation. Give that a try. Right, so let's attempt this question. Of course, we do the same thing we do every single time. We put it into fixed point first of all. So I'm going to do the units. 1, 2, -4, half, a quarter, and an eighth is what I'll need to represent this value. So to make 2 and 5/8, we'll have to do that positive first of all. So here we go. Half is 4/8, and an eighth is 1/8. So half an eighth and 1/8 is half. 4/8 plus 5/8. Anyway, that's how we get there. And we have to turn this into negative, so we have to flip it to make in 1 complement. And then we have to add 1 to the least significant bit. And so that gets us our value of this. And we can check to see if we're right, because we can say -4 plus 1 is -3, plus a quarter is -2 and 6/8, plus an eighth, -2 and 5/8. And then to turn this into standard form, we'll move this twice to the right, to the left, rather. Once, twice, 1.01011, 4-bit mantissa. If I've gone 2 to the left, does it make the mantissa bigger or smaller? Smaller, so therefore the exponent has to become, there you go, and by 2, 4-bit, so I can go 0, 0, 1, 0, because it's twice. 1, 2, 3, 4, 5, 6. That's a 6-bit mantissa and a 4-bit exponent. And if we wanted to write it out in the format that you find on the computer, we'd write it. I do appreciate I've just fallen off the side of the thing, like so. Okay, people, and now we're looking at doing it in the other way around. We're taking a floating point number and turning it into denary. A real binary number, again, so that's real in the sense that it's decimal places, has a fractional component, may be represented in a normalized floating point by using 5 bits for the mantissa, followed by 3 bits for the exponent, both in 2's complement. And we need to get the denary value of this. So remember, 5 bits for the mantissa, 3 bits for the exponent for this one, and the same for this one. It's a bit small, so maybe if I can do this, nope, that's not helpful. If I do this, it's slightly better, because at least you can see it all. Yeah, maybe easier to read. And you're attempting parts 1 and parts 2. Okay, so we need to remember the format, 5-bit mantissa, 3-bit exponent. So I'm going to write out the mantissa in green here. So it's going to be the first 5 bits. There you go. And we can say that the point is between the first 2. And the exponent, which I'll write in red, is that. Now that's going to be the value of 3. To put it back into fixed point, to allow us to get the number, essentially we need this exponent to come down to 0. So if we want to have the exponent become smaller by 3, if the exponents will become smaller, we need the mantissa to become larger. And to become larger, we got to go to the right. So if we want to come down that by 3, this needs to go once, twice, 3 times to the right, which I'll just draw now. Once, twice, 3 times. And then I can rewrite my mantissa 0, 1, 1, 0, 0. But the point is now here. And I can do my little grid 1, 2, 4, -8, leaving us with a value of 6. Let's do the other one. And the other one's got some pitfalls because it's a negative number and negative mantissa and a negative exponent. So this will be interesting about how we tackle this question. In fact, if I just go like this, but same deal in the sense that it's a 5-bit mantissa and a 3-bit exponent. So what we've got here is 1, 0, 1, 0, 0. That's my 5 bits. Sorry for some of my zeros starting to look like 6s. And we've got the same deal here with a 3-bit exponent that I'm going to do in red. Now, bear in mind, that's going to be in 2's complement. So actually my exponent's going to be -1. And so my point was here. And then what's going to happen is I'm going to have to move my point over onto here. Now, this is the bit where we have to be careful, and I believe Elijah was talking about this just now. If we make it 0.101, i.e. I've just taken this section, written it down here, and put 0 here, what have I just done to that number? Made it positive. Now, should a negative number suddenly become positive just because of this? No. So, I'm going to, on this case, what am I going to end up doing? Adding a 1, so that it's still going to be a negative number for me. So I'm going to have to do so now it's in, what's it in now? It's in, because we've brought the exponent down to 0, it's in fixed point, so we'd have to do the thing. Hey, what's this going to be then? This unit's going to be -1, and then a half, and then a quarter, and then an eighth, 16th, but we don't need those ones because they're not containing useful information. So -1 plus a half, negative a half, plus an eighth. So we've got negative equals negative 3/8. There we go. So we're having a look now at doing floating point arithmetic. This is generally one of the more challenging elements to doing this sort of subtopic. Got there eventually. And we have to demonstrate subtraction in this case of the two numbers below, so these two numbers. Both are stored in a normalized floating point format, 6-bit Mantissa, 4-bit exponent, and show the results. Now, truthfully, there's two ways of doing this. I've never actually shown you how to do subtraction directly, but subtraction follows all the same rules that you can do, like did you learn it as bus stop maths when you were little? For subtraction? You can do that directly, but I've always taught you how to just put it into 2's complement, negative, and then add it. Now the reason I'm doing that is because I think first of all it's making you practice 2's complement, making a number into 2's complement, but it's also allowing you to practice the addition that way, because that's how a computer would do it. So I'm expecting to do it in 2's complement. I just pointed out to you that you could also do it directly as subtraction. Okay, so what we're doing now is we're having a look at this question. To do arithmetic on floating point, the first thing we want to do is have both our values into fixed point. So let's do that. By fixed point, what we mean is that we're going to want to bring this exponent of 0100 has to come down to 0. So that's 4. For the exponent to come down to 4, I become smaller. We're going to have to make the Mantissa larger. So the point was here. So what we're going to need to do is for it to come over. So I'm going to write it out, the Mantissa. Oof. There you go. I'm going to write it out. 010010. The point was here, so it's going to be once, twice, 3 times, 4 times. So in fixed point, the value will be 10010 with the point here. And with the other one, we're going to have to do a similar sort of deal. We're going to have to take 010010. There's a bit deja vu here. But now we're dropping it from 2 down to 0 because the exponent's now 2. And we're going to have to go once, twice, and now in fixed point, we can go 0.010. Now bear in mind, we're trying to take away. Now you can do that directly using sort of bus stop maths as discussed earlier, but what we're going to do is that we're going to turn it into 2's complement. We're going to turn that into a negative value, and then what we'll do is we'll add, so we're plus now, but add a negative. So we'll turn that into 2's complement. So we'll do that by flipping all the values, 101.101. We have to add 1 to it, so plus 000. Oh, by add 1, I mean add one of the least significant bits. In this case, 1 and 1 is actually going to make 2, so we'll carry it over to this one here. 101. So that's our value. And now what we're going to do is we're going to have to write out our 2 different values we're going to be adding together. So we're going to be adding 01.0, and the other one is 101.110. Now this is the point of maximum possible mistakedness, where we can make a quite elementary error, and let's discuss what that's going to be. Currently the units are like this. On this side, half, a quarter, and an eighth. And on the other side, we've got 1, 2, 4, 8, and the most significant bit will be negative, i.e. negative 16. Here's what's happened. This number here is 9, positive 9, and it was a positive number, and I've made this other number, I've made it negative. Unfortunately, what I've actually done here is it's a 1 not a 4, 1 not a 1, and a half and a quarter, so I made it 5 3/4, which was not my intention. I've made my negative number positive. And so to actually bring this back into being negative, I'll need to pad with 1s on this side, and now it's going to be negative 16, negative 16 plus 8, negative 8 plus 1, negative 7, minus a half, so negative 6 1/4, I think. Over here, I need to also pad, but I'll be padding with zeros. And now I can add these two values together, hopefully successfully. So we're going to have 0, 1, 1. This one will be 2, so it'll be 0, carry the 1 into this one here. 1, 0, carry the 1 over to this one over here. Now, this number is clearly far larger. So you're having a large positive number taking away a much smaller negative number. Therefore, in the end, we should end up with a negative number. So this one over here, where you might consider an overflow, actually in this case, it's having to just be pushed off the edge, because ultimately, otherwise, how can you ever make it a negative number, a positive number? You can't. And so our answer would be, in this case, this value here. But of course, we have to put it back into the same format of 6-bit Mantissa and a 4-bit exponent. So I'm going to rewrite this up here. So it will be 0, 1, 1, 0, 0.110. I have to move the point in which direction? To the left, to normalize, once, twice, 3 times. So I'm going to write it out again. 0, 1, 1, 0, 1, 1, 0 with the point here. I've moved it 3 times to the left, making the Mantissa smaller by 3, so the exponent should be positive 3. So that should be 0, 0, 1, 1. It's a 6-bit Mantissa. Is that a 6-bit Mantissa? 1, 2, 3, 4, 5, 6. So this one here is going to go. And God, it has. And then to write it out in the same format, I should write it out as 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, i.e. that one's down here, that one's down here.